If I can't picture it, I can't understand it. Albert Einstein. Welcome, students. Today, in the methods of work, energy, and power, we discuss conservation of mechanical energy. Till so far, we have studied how to apply work energy theorem on a single particle and on a system of particles. We extend the same idea of what we have learned to explore the conditions under which mechanical energy will remain conserved. In this context, we have to pay special attention on the two types of forces, the conservative forces and non-conservative forces. Now see on this screen, you can a diagram. Here, this diagram is of a roller coaster, and at first sight it appears that if the car is released from here, it will reach at this height. Now the question is whether this car is capable of encircling this vertical loop or not. For that purpose, we have to ensure that at this top point, whether the conditions are fulfilled or not. For that purpose, we have to apply Newton's law here. And you know very well that to complete the vertical loop, at this top point, the minimum speed of the car must be square root of g into r, and r is the radius of this loop. So, in nutshell, what we can say, energy methods will suggest possibility of a process. They will not confirm whether the process will happen or not. To confirm a process to happen or an event to happen, we have to ensure that the conditions are fulfilled or required conditions are fulfilled at every instant during the process. Now, as we have seen that today under this talk, we have to explore first about conservative and non-conservative forces, because these are the only conditions which decides whether the mechanical energy will remain conserved or not. So let us discuss first conservative and non-conservative forces. Conservative and non-conservative forces. Work done by all the internal forces of a system can be divided into two categories on the basis of associated process of energy conversion, either from mechanical to mechanical or from mechanical to other forms of energies or vice versa. Actually, the internal forces of system can convert energy from mechanical to mechanical. It means from potential to kinetic or kinetic to potential, or they are converting the mechanical energy of system to some other forms and expelling it out of the system, or they are fetching energy from other forms and converting it into mechanical form. In the first condition, if the internal forces, some of the internal forces are converting the mechanical energy of the system into some other form, it means they are causing loss in the mechanical energy of the system. On the other hand, if the internal forces, means some of the internal forces, are converting some other form of energy into mechanical, it means they are causing a gain in the mechanical energy. Actually, at this talk, it is clear that this second category of forces are making mechanical energy not to conserve. So they are classified as non-conservative forces, and those internal forces which are involved in the energy conversion from mechanical to mechanical means from potential to kinetic or kinetic to potential, they are classified as conservative forces in classical mechanics, or you can say in Newtonian mechanics. Accordingly, all the forces are divided into two categories that are known as conservative forces and non-conservative forces. Now let us come on the formal definition of these forces. These forces, conservative forces, work done by a conservative force involves energy conversion from mechanical to mechanical, that is from potential to kinetic or vice versa. And now this is the concept of conservative force, and at present we can say treat it as a definition, but later in the next lecture we develop some mathematical definition how to identify of the conservative forces. But at this side, at this juncture of time, this much of understanding about conservative forces is sufficient. In this way, these forces do not change the total mechanical energy of the system. That is, conserve the total mechanical energy. Therefore, the name conservative comes. And this is why you can say these forces called conservative forces. Now we come on the non-conservative forces. As a concept of conservative forces is concerned, means they are involved in energy conversion from mechanical to mechanical, means they are keeping the total mechanical energy of the system intact. The non-conservative forces must be capable of changing the mechanical energy of the system, and this change may be either gain in the mechanical energy or loss. So let us come here. Work done by a non-conservative force involves energy conversion from mechanical to other forms of energies, or from other forms to mechanical. If some internal forces are converting mechanical energy of system to other forms, it means they are causing loss in the mechanical energy. And if they are converting some other forms of energy into mechanical, means they are making a gain in the mechanical energy. These two kinds of forces are known as non-conservative forces because they are not conserving the mechanical energy system. Usually, we encounter a force friction that dissipates mechanical energy of system as a heat or sound. On the other hand, if there are some chemical reaction system, suppose there is some motor or some engine and fuel is burned, so chemical energy released in the burning of the fuel, some part of it is converted as mechanical energy, so there is gain of mechanical energy. So these internal forces arising due to combustion or burning of the fuel, they will be treated as non-conservative forces. The energy conversion from mechanical to other forms is accounted as loss in mechanical energy of a system, whereas the energy conversion from other forms to mechanical is accounted as a gain in the mechanical energy of the system. And this idea is very obvious. And as I explained earlier, if the non-conservative internal forces are converting mechanical energy of system to other forms, it means they are making loss in mechanical energy. And if these internal forces are converting some other forms of energy into mechanical, it means they are making gain in mechanical energy. So non-conservative forces may increase the mechanical system as well as they can decrease the mechanical energy of the system. Thus, when non-conservative forces do a non-zero work, the mechanical energy does not remain conserved. So that is key idea behind non-conservative forces. And here pay attention, when all the non-conservative forces do a non-zero work, only when they will change mechanical energy of the system. Now we summarize what we have learned so far. A form of energy other than mechanical is frame independent. Therefore, the total work done by a non-conservative force pair is frame independent. That is very, very important idea. Say, any other forms other than mechanical energy, say sound energy, heat energy, all these energies are independent of frame reference in Newtonian mechanics. If they are independent of frame reference, it means the work done by these non-conservative forces, total work done, here you see the term here, by a non-conservative force pair. Actually, a force will exist in pairs because a force is always two-body interaction, and I am taking all the non-conservative forces internal of a system. If I am saying all, it means it's a force, non-conservative force, and a reaction. Both are included in the system, so they are called internal forces. So their total work, the total work of a pair means all such pairs, if you 8, that total work will be independent of frame of reference. And it means we can say very simple example. If kinetic friction is an internal force of a system, the work done by this kinetic friction or energy lost will be frame independent. This idea sometimes becomes very useful in solving problems. Now we pay attention on the total work of internal forces on a system. We have identified till so far what conservative forces will do and what non-conservative forces will do. Now we see some more discussion about total work of all the internal forces of a system. Total work done by all the internal forces of a system can be divided into two categories, that are the total work done by all the internal conservative forces and the total work done by all the internal non-conservative forces. This idea we can express mathematically. Summation dW internal is equal to summation dW internal conservative plus summation dW internal non-conservative. Here I am considering an infinitely small interval. And what does it mean, summation? It means dW internal is work done by an internal force, and summation means all internal force in a very small time interval. Similarly here, dW internal comma conservative denotes work done by a conservative force in a very small interval, and here this summation denotes sum of work done by all such internal conservative forces, and same is applicable here for internal non-conservative forces. Here we can extend in integral form. Summation W internal is equal to summation W internal conservative plus summation W internal non-conservative, and this is statement applicable for a finite interval of time or space, and this equation is applicable for an infinitely small interval. Now we discuss on total work of internal conservative forces, because here we have seen the total work of all the internal forces can be classified or can be divided into two categories, that is work done by all the conservative internal forces and work done by all the non-conservative internal forces. So let us see, first discuss total work of internal conservative forces. And you can recall the work done by conservative forces is decrease in potential energy, that is definition of potential energy, and we mix this idea, we apply now this idea here. Total work done by all the internal conservative forces is equal to the decrease in potential energy of the system. So that is very fundamental idea, and it makes things simpler to execute, because instead of calculating total work done of all the internal conservative forces, we account them by decrease in potential energy of the system, total potential energy. So what we can say here, summation dW internal conservative is equal to minus du. Again, this is applicable for a small, infinitely small interval. Again, I say, what is dW internal conservative? That is work done by an internal conservative force, and summation is all internal conservative force over a very small time interval, infinitely small, and that will be equal to minus du. du is total potential system decrease. Now we can write this equation in integral form. Summation W internal conservative is equal to minus summation U final minus summation U initial. What does it mean? Summation U final means total final potential energy of system, and summation U initial total initial potential energy of system. As see this expression, basically mathematically it is called increase, and putting a minus sign here, it means it is called decrease mathematically. So it will be here, if you open the bracket, so it becomes summation U initial minus summation U final. So in this way we can account the total work done by all the internal conservative forces as decrease in potential energy of the system. Now we pay attention on the total work of internal non-conservative forces. Total work done by all the internal non-conservative forces is either loss or gain in mechanical energy of the system. This idea we have discussed recently, that total work done by all the internal non-conservative forces will be either equal to gain in mechanical energy or loss. If these forces are converting mechanical energy into some other form of energy, it means they are causing loss in the total mechanical energy. If these forces are converting some other forms of energy into mechanical, it means they are making a gain in the mechanical energy of system. Now we extend these ideas of total work done by internal conservative forces and internal non-conservative forces to work in a theorem for a system of particles, and see what kind of improvement these ideas are making in the use of that theorem. More about the work energy theorem. of a system of particles or system. So let us discuss the formal statement of theorem what we had learned it previously. Summation W external plus summation W internal is equal to summation K final minus summation K initial. That is work done by all the external forces plus work done by all the internal forces means what is this left hand side suggest? Total work done by all the forces of a system is equal to change in kinetic energy of the system. Summation K final means total final kinetic energy. Summation K initial means total initial kinetic energy system. So this is what statement of work energy theorem. And let us call equation number 1. Expressing the total work done by all the internal forces as sum of the total work done by all the internal conservative forces and the total work done by all the internal non-conservative forces we get. Actually, previously we have seen that this work done by total internal forces can be divided into two categories. What? Total work done by all the conservative forces and total work done by all the internal non-conservative forces. So we break this term into two. Let us see here. Summation W internal is equal to summation W internal conservative plus summation W internal non-conservative. Let us say equation number 2. So this idea we have explored recently. Now total work of all the internal conservative forces is equal to decrease in potential energy of the system, and this idea we also seen. So in this way this term can be expressed as summation W internal conservative is equal to minus summation U final minus U initial, or summation U initial minus summation U final. Let us say equation number 3. Now total work of all the internal non-conservative forces is accounted as gain or loss in mechanical energy of the system, and this we have seen earlier also. So now we have these three equations and this idea. So if we combine all these four ideas, these three equations and this one, now we can summarize how this equation will change. Combining all the above ideas, we get summation W external plus summation W internal non-conservative is equal to K final plus U final minus K initial plus U initial. What we have done? Actually, we have substituted this two terms for this, and for this we have substituted this, and for these two terms we have brought from left hand side to right hand side, and we get this. So what we are obtaining here, work done by all the external forces plus work done by all the internal non-conservative forces is equal to, if you pay attention here, you can see it is total mechanical energy final of the system. It is total initial mechanical energy. So instead of this we can write E final or E initial. So we denote the total mechanical energy by E, and in this way we can rewrite the equation denoting the total mechanical energy summation K plus summation U of a system by E. We have summation W external plus summation W internal non-conservative is equal to E final minus E initial. So that is a final or general statement of Work-Energy theorem. What? The total work done by all the external forces on the system plus total work done by all the internal non-conservative forces within the system will be equal to change in total mechanical energy of the system. So here we are writing the statement: total work done by all the external forces and all the internal non-conservative forces is equal to the change in mechanical energy of a system. So this idea will refer as general work energy theorem for a system. And here what we have done, simply we have divided this total work done by all the internal forces into two parts: total work done by all the internal conservative forces plus total work done by all the internal non-conservative forces. Again we are using the definition of potential energy, that total work done by all the internal conservative forces will be equal to decrease in potential energy. And combining all these ideas we get this statement, and what I have said there, this we will refer as general work energy theorem. The above statement is a general statement of work energy theorem applicable to a system in classical mechanics. I am saying it Why classical mechanics? Because sometimes you might have heard about mass energy conversion. Such kind of process we are not including here. The statement expressed in differential form. Now this statement is in integral form. We can express this statement in differential form also. So what it will be? Summation dW external plus summation dW internal non-conservative is equal to dE. Now we can have very important thing. If you divide the entire equation, every term by dt, so we get the same theorem in terms of power. Dividing by dt, we get, this will be what? Total power of external forces. This will become total power of internal non-conservative forces. That is what? Time rate of change in mechanical energy. So in this way, the working theorem for a system particle or system, we can express in terms of power also, in a differential form as well as in integral form. Differential form is for an infinitely small interval. Integral form is for a finite interval. Conservation of mechanical energy of a system. Now we are equipped enough to understand what is the conservation of mechanical energy and under what condition mechanical energy of system will remain conserved. Now if you see the general statement of work energy theorem, if total work done by all the internal non-conservative forces and all the external forces will be zero, we can say mechanical energy will remain unchanged. It doesn't mean that it will remain conserved. For conservation, in every infinitely small time interval, the energy must be unchanged. So this statement will express in differential form. If in a time interval, total power of all the external as well as internal non-conservative forces of a system is zero, the total mechanical energy of the system will remain conserved in that time interval. Now see, attention here, I'm saying power. Power is again instantaneous. So here conservation means at any instant of time mechanical energy of system is not changing. So what we can say, total power of all the external forces as well as internal non-conservative forces is zero at every instant in a time interval, only when in that time interval total mechanical energy of the system will remain conserved. So we can write here summation P external plus summation P internal non-conservative equal to 0. It means dE by dt is 0. So time rate of change in mechanical energy will be 0. And we can extend it, dE is equal to 0 here. If dE by dt is 0, it means d is 0. d is 0 means in integral form, delta is 0 means finite change in mechanical energy will be 0. And we can express further, it is summation delta k plus summation delta u is equal to 0 means total change in kinetic energy plus total change in potential energy of system will be 0. Or we can say here E initial is equal to E final. And again summation k initial plus summation u initial is equal to summation k final plus summation u final. So all these are alternative forms of conservation of mechanical energy. Depending on situation, any other form we may use. And one more thing, very peculiar use or peculiar condition, that if there is no external force and there is no internal non-conservative force, under that condition mechanical energy will remain conserved. Actually this is the situation, of course very hypothetical, it can never happen in actual practice, but to explain the idea, in most of the textbooks the problems which are taken or the problem exercises which are given, they involve this situation. So under that condition, what is statement generally given? If there is no internal non-conservative force and there are no external forces on a system, its mechanical energy will remain conserved. What I personally feel that this is a very hypothetical case, and I'm not referring that case. Of course in this condition mechanical energy will remain conserved, but here we are making a very general statement that if total power of all the external forces as well as that of internal forces will be 0 at every instant of time, that in the concerned time interval total mechanical energy will remain conserved. So here situations very common in textbook problems involve absence of external forces as well as internal forces or internal non-conservative forces. In such situation, mechanical energy remains conserved. Actually, that is a very narrow idea, and here we have generalized the idea because if you see, in actually we are not always have to solve the textbook problems. Basically, we have to solve practical problems also. So, in any practical situations, external forces may be present, and internal non-conservative forces may be present. But if their total power will be zero, then mechanical energy will remain conserved. So, we have seen what is the idea of conservation of mechanical energy in detail. The law of conservation of mechanical energy of a system is a special case of the fundamental law of nature, that is conservation of energy, where exchange of energy with the surrounding, that is conversion of mechanical energy into other forms or vice versa, and or mass energy conversion is not permitted. Actually, if you look very carefully or very deeply, that conservation of mechanical energy is a special case of more general principle, that is conservation of energy under what conditions? Exchange of mechanical energy of the system with the surrounding is not permitted, and mass energy conversion is not permitted. That's why I was mentioned earlier that what the ideas we are discussing, they are applicable only to classical mechanics or Newtonian mechanics. Now we are in a condition to apply what we have learned to some example problems. Let us see the first example. An artificial satellite of mass m is revolving around the Earth in a circular orbit of radius small r. Assume capital Z, m and r to denote universal gravitational constant, mass of the Earth and the radius of the Earth respectively. What are we to find? A. Develop expression for the orbital velocity V naught. Actually, we have to explore something about energy of satellite, so we must know its orbital velocity. Of course, to find orbital velocity, energy method are not required. For that, we have to use Newton's law of motion. And to find here orbital velocity means with what speed satellite is moving in a particular circular orbit. For that, we have to use Newton's law. So, how we can use? In a circular orbit, the gravitational pull of the Earth provides the necessary centripetal force to the satellite. Hence, we have this way. Now just see, that is the Earth, and on this circular orbit, this satellite is moving, and say its speed is v naught, and radius of the orbit is r. We apply Newton's law. So we know that only force acting on the satellite is the gravitational pull of the Earth. We can say F subscript g, and that is equal to, again in circular motion we resolve all the forces and effective forces in terms of tangential and normal component. So here there is no tangential force, so there will be no tangential acceleration, only centripetal acceleration. So for satellite, if speed is v, the centripetal acceleration is what? mv naught square by r. So what we can write here, by Newton's law, Fg is equal to mv naught square by r. So here summation Fn is equal to man, and for Fg we can write Newton's law of gravitation, G capital M small m by small r square. So G mm by r square is equal to mv naught square by r. So from here we can find the orbital velocity. V naught will be square root gm by r. So in this way we have found orbital velocity. Now, knowing the orbital velocity, we can write the kinetic energy of the satellite. Now in second part, we write the total mechanical energy of the system or this satellite. Write expression for the mechanical energy of the satellite. So we know that mechanical energy is equal to sum of potential energy and kinetic energy. Knowing this orbital velocity, we can write the kinetic energy. And in previous lecture, we have developed what is potential energy of the satellite minus gmm by r. Here r is the distance of satellite from the Earth center. So by adding these two terms, we can write the total mechanical energy. So here kinetic energy, that is half mv naught square. So this will be simply half mv naught square, and substituting this v naught, what we get? K is equal to g mm by 2r. And it is very simple, you can verify it. And what is the gravitational potential energy? That is U is minus gmm by r. Now if we add them, we can will obtain the total mechanical energy. Mechanical energy, that is E is equal to K plus U, and that is simply minus gmm by 2r. So this is the total mechanical energy of the satellite. Now in part A we have obtained the orbital velocity, and part B the total mechanical energy. Now we can use some situation, we can take some situation where conservation of mechanical energy or an mechanical energy, that is work energy theorem on a system is applicable. So let us see, say the C part. It is desired to double the radius of the orbit. For the purpose, a rocket in the satellite is switched on. Find the work done by the rocket. Now just see, if rocket is switched on means there is some fuel in the rocket that will burn, and the chemical energy released in the burning of the fuel, some part of it or full part of it will be utilized in increasing the radius of the orbit. So let us extend the idea here. Work energy theorem for the Earth satellite system. First we solve this problem by using work energy theorem, that is general form of work energy theorem. For this we will first explore what are the internal and external forces. If we consider the Earth and satellite as a system, the work done by all the external and the internal forces must be equal to change in mechanical energy of the system. That was the theorem. So we have to explore what are the internal forces and what are the external forces. Again, what are the internal conservative forces and what are the internal non-conservative forces. There is no external force on the system, and now no work by external force. Of course, if you include Earth and satellite as a system, there is no external force. Of course, the gravitational pull of the Earth on satellite is internal force of that system, because the satellite is applying equal opposite pull on the Earth also. And what are the internal forces? So let us see here. The internal, or you can say interaction forces between the ejected burned gases and the satellite, working as a non-conservative force, provides a portion of the energy released in burning of the fuel as mechanical energy to the system. Thus, it is considered as work done by the rocket. Actually, when fuel is burned, some chemical energy released, and here first I'm saying that some part of that energy released is converted into mechanical energy, and in this way, that is if it is energy is converted into mechanical energy by concept of work, that is transfer of mechanical energy, so it will be assumed as a work, and this work is known as work done by the rocket. Of course, the interaction forces between the ejected gases and the rocket are internal force of system, and they are non-conservative because they are involved in the energy conversion from chemical to mechanical. They are increasing the mechanical system, so they are non-conservative internal forces. Again here, employing the above ideas and the expression of the mechanical energy of the Earth satellite system obtained in the previous part, in the general work energy theorem, for a system we get, so what the general work energy theorem we have written here, work done by all the external forces plus work done by all the internal non-conservative forces is equal to increase in mechanical energy. Here there is no external force, so work done by all the external forces will be zero. Work done by all the internal non-conservative forces we will call work done by rocket, and that we have to find, it is unknown. And mechanical energy expression we have obtained in the previous part. So what we can write here, summation W external plus summation W internal non-conservative is equal to E final minus initial. If we know that this is 0 and this is work done by rocket, so we substitute here 0, here work by rocket, and E final minus initial. Mechanical energy we have obtained in previous part, that is mechanical energy at any radius orbit r is minus gmm by 2r. So let's substitute here 0 plus work by rocket is equal to this final energy minus gmm by 2, and what is 2r? Because radius is doubled, and for initial minus gmm by 2r, and by solving this we get work done by rocket is equal to gmm by 4r. So in this way you obtain the work done by rocket. Now we have taken the first example where energy mechanical was not conserved, because what I said you, that is in typical textbook problems, or most of the textbook problems, they are designed to make a student learn the conservation of mechanical energy. So they are artificially creating the conditions, or they are assuming conditions in which mechanical energy will remain conserved. But what I said here, practically we'll seldom find a situation where mechanical energy will remain conserved. So here we have used work energy theorem general form. Now let us see, we apply the same, that is work energy theorem on a satellite. We are not using system approach now. We apply work energy theorem to a satellite, then see what will happen. It is desired to double the radius orbit, means the C part of the equation is again reproduced here. So what is the approach? Work energy theorem for the satellite. It means we are applying now work energy theorem to the satellite only. We are not considering any system. So that theorem is very simple. Work done by all the forces acting on the satellite must be equal to change in kinetic energy of satellite. So if we apply work energy theorem on the satellite, the gravitational pull of the earth and interaction of forces from the gases being ejected by the rocket are to be considered as external forces, because now gravitational pull of the earth on the satellite will also be external force, and interaction of the rocket with the gases being ejected, what force is creating with that interaction, will also be considered as external force on the rocket. And we know that the work done by this external force, interaction with the gases, is work done by rocket. And work done by gravitational force can be considered as decrease in potentiality of the satellite Earth system. So in this way we can calculate it very easily. The work done on the satellite by the interaction forces from the gases being ejected by the rocket is the work done by the rocket. We have seen it earlier. And next idea, the mass of the gas ejected can be neglected as compared to the mass of the satellite. Of course, how much gas is ejected, that we neglect. So that's why before burning of the fuel, or before switching on the rocket, what the mass satellite was having, we consider same mass after the radius has been doubled. So how much fuel has been expended in this process, we are neglecting the mass of that fuel. Initial and final kinetic energies of the satellite, so we can write it very easily. So what is K initial? Gmm by 2r. What is K final? Gmm by 2 into 2r, or Gmm by 4r. And this expression we obtained in the part B. And work done by gravity on the satellite, this we can consider as decrease in potential energy of the Earth satellite system. Why? Because equal force is acting on satellite as well as on the Earth. But as compared to satellite, inertia of the Earth is infinitely large. So with that force we consider the Earth will not move at all. Only satellite will move. So this force pair, the force acting on the Earth is not doing any work. Only which force is doing work? The force, the pull on the satellite, because satellite is moving, Earth is almost stationary. So in this way, to calculate the work done by this force, we can consider decrease in potential energy. So work done by gravity is equal to U initial minus U final, decrease, initial minus final. Pay attention here. So it will be minus Gmm by R minus Gmm by 2R. So what we get here? Minus Gmm by 2R. So that is I can see here it is minus Gm by R. So here plus Gm by 2R. So what we get? Minus Gm by 2R. Now we substitute these ideas in work energy theorem. Substituting these expressions in the work energy theorem, what we get? W initial to final is equal to K final minus K initial. This is formal statement of work energy theorem, that is work done by all the forces acting on satellite, that is final kinetic energy and initial kinetic energy. In work done by all the external forces is the work done by gravity plus work done by interaction forces with the rock ejected gas. And this second term, work done by interaction forces with the ejected gas, is we know that is work done by rocket. So what we substitute here, work done by gravity plus work done by rocket is equal to K final minus K initial, and for this what we substitute, minus m by 2r, and this we have to find, and these two values we are having here, so let's substitute here. So minus gm by 2r plus work done by rocket is equal to gm by 4r minus gm by 2r. Now solving this, we get the same answer what we obtained in the, by previous method. What work done by rocket is equal to gm by 4r. Now today we'll take few problems and we apply both the ideas, conservation of energy or work energy theorem in general form, and if it is possible to apply work energy theorem on a single body, and try to develop an understanding where we to use which method. So at present I will not lay down any preference of selecting the method, just I am discussing all the ideas. So this was the question on satellite. Now we take next example. Let us see what in this example is. A block of mass 0.5 kg slides from the point A on a horizontal track with an initial speed of 3 meters per second towards a weightless horizontal spring of length 1 meter and force constant 2 Newton per meter. The part AB of the track is frictionless and the part BD has coefficient of friction, static and kinetic, as a 0.22 and 0.20. The distance AB and BC are of 2 meter and 2.14 meter respectively. Find the total distance set by the block before it comes to rest. So this setup is given here. The length of this spring, relaxed length is 1 meter, and here is the block, and its initial velocity is shown, how much, 3 meters per second toward the spring, and this track part AB of length 2 meter is frictionless, and from B to D, from here to here on this track there is friction, and coefficient of static friction is 0.22 and coefficient of kinetic friction is 0.2. Now we just see, find the total distance slid by the block before it comes to rest, means when the block will come to a final stop, how much distance it has slid totally. So what we think first, work energy theorem for the spring mass or spring block system. So we consider spring and block as a system. So if you include here, and for that if you are including this considering a system, so first we explore what are the internal forces and what are the external forces. You can see very well, gravity of on the block, its weight is external force, normal on the floor is external force, but a spring force between the block and this end of spring is internal force. But if the block is pressing the spring is applying force here also, and the spring is will press the wall also, and the wall will also press the spring. So this force by wall on this end of the spring will be considered as an external force. So let us see these forces. If we consider the block and the spring to be a system, the external forces are weight of the block, friction from the floor on its portion BD, and reaction of the wall on the spring during compression spring, and of course there must be normal action also. Let us show all these external forces. So on this portion A to B, say here, the external forces are weight and normal action because this is frictionless. Now from B to C, before it strikes the spring, there are three external forces, weight mg, normal action that will be equal to mg, and force of kinetic friction because it is sliding. Now after it will touch the spring, so here it will compress the spring. So what are the external forces on the system? Weight, external force, normal action, and this kinetic friction, and the force applied on this end of the spring force FSCL. So these are the external forces of the system. So please pay attention here on this part. Here the spring force is internal for a spring block system. Now let the block stops for a moment compressing the spring by an amount x. what do we say? By compressing by an amount, let us say the block stops for a moment. Means when the spring compression will be maximum, block will stop. And if at that instant limiting friction will, if more than the spring force, the block will remain at rest here, so it will come to a permanent stop. But if the force of limiting friction is less than the spring force, the block will move back. Now let's see that we compare whether the block will remain at a permanent stop or not. We'll see later. First we find how much it will compress the spring. Initial and final mechanical energies. Of course, what we are saying here, we are using work energy theorem on a system of block or system. So we are using general theorem. What? Work done by all the external forces plus work done by all the internal non-conservative forces is equal to change in mechanical energy of the system. So we find initial and final mechanical energies. So initial is K initial plus U initial. U initial is 0 and so it is half mv I square. Similarly, we can write final, E final, K final plus U final. So K final is 0 here, U final half kx square, because we are assuming the spring to be compressed by amount x. So this energy will be stored in the spring as potential energy, and we have included spring in the system. So this is, we are calling this potential energy. So that is initial mechanical energy, that is final mechanical energy. Now total work done by all the external forces. So that is summation W external will be some Wg plus Wn plus W friction plus Ws. S is spring force here on this end of the wall. Again, pay attention. So now if you see, work done by gravity is 0 because the entire movement of the block is perpendicular to gravity. Similarly, work done by normal is 0 because the entire movement of the block everywhere, every instant of time, it is perpendicular to normal direction. And work done by friction, that is kinetic. So this friction is constant. So this will be equal to minus frictional force, that will be mu mg, because n is mg. So friction is mu mg. So minus mu mg, and total distance slid by the block, that is portion AB plus portion BC plus x. So what is AB plus BC? You can add them. Let us write here. So we write it, on AB there is no friction, so only BC. So BC plus x. So this will be minus mu mg into BC plus x. Now what is work done by spring force on this end? 0, because this end is immobile. It is the same idea what we had taken in the previous problem, where when we are considering work done by gravity, when we have taken Earth and satellite as system. So gravity was acting on satellite also, and gravity was acting on the Earth also. But as inertia of the Earth is infinitely large, so Earth is not move, only satellite will move. So work done by gravity on the Earth was 0. So total work done by gravity was on the satellite. Similarly here, work done by spring force at this end will be 0, because this end remains stationary. Let's substitute value 0 plus 0 minus mu k mg bc plus x. By mu k we are denoting the coefficient of kinetic friction, and this is also 0. So this is what? Minus mu k mg bc plus x. So we have done obtained work done by all the external forces, this, and for this system internal forces work done. What we can see, there is no internal non-conservative force. Of course, this Fk was non-conservative, but it is external to the system. So what was our theorem? Work done by, total work done by all the external forces plus total work done by all the internal non-conservative forces equal to change in mechanical energy. Here you can see there is no internal non-conservative force. Of course, friction is an external force. So total work done by all the internal non-conservative forces will be 0. So we write here summation W internal non-conservative is 0. Now we substitute all these expressions in the general form of work energy theorem. So let us see what we get. Substituting the expressions obtained in the general work energy theorem for a system, we get, what is the general theorem? Summation W external plus summation W internal non-conservative is equal to E final minus initial. I am again saying the theorem, that is total work done by all the external forces plus total work done by all the internal non-conservative forces will be equal to change in mechanical energy system. Now we obtain this one and this one. Let us substitute the values. So what this was minus mu kmg bc plus x, and this is 0, and it is what half kx square minus half mvi square. Let us call equation number 1. And why I am calling equation number 1? Because we solve this problem by some other method and compare this equation. So what we get here, MQL is minus 0.2, mass is 0.5, G is 10, BC is 2.14, X we have to calculate, half K is given 2 Newton per meter, X square, and that is again half M, mass is 0.5 kg, 3 square. Now by solving this, what we get, X square plus X minus 0.11 is equal to 0, and we can find roots of this equation, and which root, that is this we obtained, of course this will be selected as X is equal to 0.1 meter. So compression of the spring will be 0.1 meter. So to decide whether the block stops permanently or slides back after a momentary stop there, we have to compare the spring force and the force of limiting friction in this configuration of maximum compression. So the spring force is Kx, F spring is Kx, 2 into 0.1, so 0.2 Newton. And what is limiting friction? Mu s mg. So Fsm is equal to mu s mg, so 0.22 into 0.5 10, it is 1.1. You can see the force of limiting friction is considerably larger than the spring force. So the block will remain at rest at this position. So what is the total distance taken by the block? Length of AB plus length of BC plus 1. So AB was 2, BC was 2.14 and 0.1. So let us add them all. So limiting friction here is more than the spring force. Therefore, the block will stop permanently. And now we can find the total distance slid. Total distance slid by the block is equal to AB plus BC plus X, and it is 4.24 meter. So that idea is, you can see, we have solved this problem by using work energy theorem on a system complete, general work energy theorem. I'm again repeating the statement. What is general statement of work energy theorem? Work done by all the external forces plus work done by all the internal non-conservative forces must be equal to increase in mechanical energy of the system. Now we solve the same problem by applying work energy theorem on the block, and finally by solving few problems by one or two possible methods, you'll be in a better condition to realize or to decide in which type of situation, which method we should adopt. So let us apply work energy theorem on the block. Work energy theorem for the block, and if you apply work energy theorem on the block, the external forces are its weight, friction from the floor on its portion BD, and spring force during the compression. Of course, normal action is also there. So we show all the forces here. So this initial setup was given. Now we show all the external forces acting on the block. So on this portion, that is mg and normal action. On this portion, mg, normal action and force of kinetic friction. And on this portion, mg, normal action, spring force, because now we are taking blocks separately. So is what spring is pushing here with this force, that will be an external force for the block, and of course force of kinetic friction during the movement of the block. So for the block, we have shown the various external forces. Now if to apply work energy theorem, we first write expression for the initial and final kinetic energy of the block. Then we calculate work done by all the forces acting on the block. And what is the theorem? Simply, work done by all the forces acting on the block must be equal to change in kinetic energy of the block. Initial and final kinetic energies. K initial is equal to half mvi square. And K final is 0 because block stops here. Total work done by all the forces on the block So Wg is equal to 0 because every time moment of the block is perpendicular gravity. Similarly, Wn will be 0. No need to any explanation. And work done by friction minus mu k mg into bc plus x. How much this compress? And work done by spring force Ws is equal to minus half kx square. Now you can see the previous when we applied work energy theorem to satellite, and now we are applying work energy theorem to block. On satellite, gravity was how we have calculated work done of gravity on satellite. Actually, we have, for that purpose, we have taken satellite Earth system, and work done by gravity total will be equal to decrease in potential energy. And again, we have seen that gravity was not doing any work on the Earth, so the total work was equal to on the satellite. Similarly here, of course, spring force is the external force, but to calculate work done by spring force, what the idea we are using? We are considering the spring block system. So work done by this spring force will be equal to decrease in potential energy. Again, these spring force on the wall and spring force on the block. Out of this, spring force on the wall is not doing any work. The total work is doing what? This spring force on the block. So this work will be equal to decrease in potential energy. So we written here. So when we are applying work energy theorem on a block, if there are any conservative force, work done of that conservative force we can obtain by this way as decrease in potential energy. So in this way we can make some simplification in the work energy theorem as applicable on a body. So now we substitute these values in work energy theorem. Substituting these expressions in the work energy theorem for a particle, we get W initial to final is equal to K final minus K initial. That is formal statement of work energy theorem for a particle or for a body. So that is Wg plus Wn plus W friction plus W spring is equal to K final minus K initial. First term is 0, 0, and this is what? Minus mu k mg Bc plus x minus half k square equal to 0 minus this. I'm again explaining this idea. So this Wg is 0, Wn is 0, work done by friction is minus mu k mg Bc plus x, work done by spring force is minus half k square. Final kinetic energy 0 here when it will have maximum compression, and initial kinetic energy was half m meter square. Now this is the same equation 1 as obtained in the previous part or previous method. We can compare this equation. We have marked equation 1 there in the previous part. Now there is no need to further solve because further calculation will be simpler, because further we are not having if we solve this problem just to find answer, we have to repeat the calculations. Now I'm again explaining you that we can use a mixture of energy conversion, work done that is work energy theorem general form and work energy theorem on a single particle. What? When you are using work done energy theorem on a single particle, if you find there is any conservative force, of course with that particle, with some other body, their internal conservative force, so work done by that in conservative force will be decrease in potential energy of that system, the body under consideration and the other body. If that internal force is not doing in work on the other body, then the total decrease in potential energy will be equal to work done by that conservative force on the body under consideration. Of course, this idea seems to be very complex when we are explaining language, but what I suggest you, by just reiterating this twisted language, that you should pay attention on this idea. Why it is that? Because the spring is doing work here and the spring is spring force acting here, but total work done by this spring force on the block plus this spring force on the wall will be equal to decrease in potential energy of the spring. But here this is not doing any work, so it will be the total decrease in potential energy will provide it to block. So again, suppose if there were, instead of wall there was another block, so this end were also moving, so in that condition we cannot use here work done by spring force on the block will not be there, so it will be work done by total work done by spring force on this block, and if what we assume here another moving block. So please take care of this idea. Now we take another example, example 3. A ring of mass small m is equal to 30 gram can slide on a frictionless fixed vertical rod. Attached to the ring, a light string passes through an ideal pulley fixed at a distance a is equal to 0.8 meter from the rod. A block of mass capital M is equal to 50 grams is suspended from the string. The ring is held in level with the pulley and released. Now just see, this setup is given. This ring can slide on this fixed vertical frictionless rod, and in the level with the ring there is a ideal pulley and a string connected with the ring here and passes here, and block capital M was suspended here. Its mass is 50 gram, its mass is 30 gram, and this distance A is given to be 0.8 meter. Now initially the ring was held at this position. Now after releasing the ring will start sliding down because at present there is no vertical force on the string, only force of gravity will start pulling it here. As ring moves down, the string will become inclined. So tension vertical component will try to retard the spring. So ultimately it will stop it. So what we have to calculate here, see first part, how far below the initial position is the equilibrium position located? So at what distance from this is equilibrium position? And we know that in equilibrium position, all sum of all the forces is zero. So we will not consider any process. Just we assume the ring has a distance, and we denote that distance by delta y subscript r for ring. And under that condition, we balance all the forces. Of course, as the ring will move down, this block will move up. So displacement of the block will denote by delta y b, b for block, and displacement of ring will denote by delta y r. So what we do here, forces acting on the block and the ring are shown in their free body diagrams. Here T and N are the tensile force in the string and the force of normal reaction from the rod on the ring respectively. Here is the initial configuration, and now we assume configuration in equilibrium. So the ring has descended distance delta yr. We show all the forces, capital Mg, weight of the block, and the string tension here. The string tension will T will act here, T, weight of the ring, small mg, and normal reaction of the rod will act here on the ring, because the string will pull the ring here and the rod will stop the ring from moving in this direction. So here with normal reaction. Now we can resolve the force into x and y component, vertical and horizontal. Only T have to resolve. So for this, let us assume this angle theta. So this component will be T cos theta, and this component will be T sin theta. Now we have, that is a translational equilibrium of the block. For the block we have summation Fy to 0, so T is equal to mg is the only equation. So summation Fy equal to 0, it means T is equal to capital Mg. Now translational equilibrium of the ring, summation Fx is equal to 0. So in x action, so what you get, N is equal to T cos theta. Summation Fx equal to 0. So what you get, N is equal to T cos theta. And summation Fy equal to 0, what you get here, T sin theta is equal to small mg. Summation Fy equal to 0, that is T sin theta is equal to small mg. Now by using this equation of y component and this equation of y component, we can eliminate T and find angle theta. So from the above equations for y components, we get that is just in place of T, what I write here, mg. So mg sin theta is equal to small mg, g and g will cancel. So sin theta is equal to small m upon capital M. So what you get, sin theta is equal to small m upon capital M. Let us substitute the values, 30 gram upon 50 grams, so it is 3 by 5. So sin theta is 3 by 5. Now we have to find this delta yr, this a is given. So if this angle is theta, you can say from here, this angle will also be theta. So from here we use delta yr is equal to a tan theta. So we have to find tan theta. So from here, and you can see very easily, tan theta is 3 by 4. Because you know that is very well known ratio. When theta is 3, sin theta is 3 by 5, angle is approximately 37, or you can say 37, and tan 37 is 3 by 4. So what we can say, the ring is in equilibrium position at a distance delta y r below its initial position, and this delta y r will be equal to a tan theta. So delta y r is equal to a tan theta. Substitute in values, 0.8 into 3 by 4, we get 0.6 meter. So from the initial position, 0.6 meter below is the equilibrium position. Now, what is B part of the situation? Actually, in this part, we have used only Newton's law. There was no use of work energy problem, or work energy theorem. And what's C in B part? Determine the distance that the ring will descend before coming to rest for the first time. So here we have to use work energy theorem. Now we first consider the ring block system, and then we use some other idea. Now you see, in two problems, we have taken very special condition, that is here in this problem, where is the equilibrium position, and in satellite problem, where is that is the orbital velocity. For these two things we have to use Newton's law. I have intentionally added these instances or these examples here because later on we, after work energy, we will find situations where we will decide in what condition, for what condition we have to use Newton's law, and for what conditions we have to use method of work energy. And we have seen earlier that whenever we decide what is happening at an instant, we have to use Newton's law. And when we decide what is happening over an interval, space interval, we have to use method of work energy. So that's why I have taken here the equilibrium position. Equilibrium position means what is happening at that position. So we have used Newton's law here. Now in this part, what? Determine the distance that the ring will descend, ring will move before coming to rest for the first time. It means a space interval and speed change. Of course, here speed change will be 0 because ring starts from rest and it stops finally. So change in kinetic will be 0. So this part involves a space interval and speed change. Of course, speed change is 0. So that is area of methods of work energy. So first use work energy theorem for the ring block system. All the external and internal forces for the system at an intermediate stage are shown in the figure. So see here, this is what the forces, the weight of the block, string tension here, that is weight of the ring, normal reaction, and support reaction on the clamp of the pulley. If you are considering the block and ring as system, so this string will be included because that is interconnecting link. And for this system, what are the external forces? Mg, because it is the interaction of the block with the earth, and earth is not included in system. This Mg is the external force by the same reason. This normal reaction will be external force because rod is not included in the system, and this normal reaction arises due to interaction between the ring and the rod. Again, this reaction at the clamp must be an external force because this support is not included in the system. So external forces are the gravity on the block, gravity on the ring, and normal reaction, and this reaction force R. And what are the internal forces? This string tension only. So external forces are capital Mg, small mg, N, and reaction at the support R. What is the internal force? That is only internal force, string tension T. So we have decided what are the internal forces and what are the external forces. Now we decide work done by various forces. Among the various forces of system, there are these external forces and these internal forces. So first let us consider work done by this internal force T. So what we can conclude here, that is of course we can calculate work done by tension on the block, then work done by tension on the ring, and sum up. But we have very simple idea here that this interconnected link from this point to that, including pulley is massless, string is massless, and again the string is non-deformable and extremely flexible. So this complete interconnected link is incapable of storing any mechanical energy. So work done by tension on this complete system will be 0. So what we can say? total work done by this interforce tension will be 0. So let us write this idea here. The interconnecting link or system that consists of the string and the pulley is incapable of storing mechanical energy. Therefore, total work of the internal force string tension is 0. That is very, we have written this very simply. So total work done of tension will be 0. Now we concentrate on work done by these external forces. The external forces R and N do no work, as the particle at which Rx does not move, and displacement of the particle at which, or particles on which, n acts is perpendicular to n. So here work done by this R will be 0 because this point is not moving. Again work done by n will be 0 because displacement is perpendicular to n. Only from external forces these two gravity forces are doing work. So if we assume displacement of the block by delta YB and displacement of ring by delta YR, we can write expression for work done by these forces. W tension is 0 and W normal is 0 and WR is 0. So what we have decided till so far here, W tension is 0 by this idea, and by these two ideas Wn will be 0 and Wr will be 0. Now we have to write work done by this gravity and work done by this gravity. For this we must know displacement of these bodies. Of course these displacements will be related because they are connected by string. So we may need to explore the constant relation between the displacement. Only gravity does work. So what we have for the work done by gravity on the block is minus mg delta yb. We assume it goes delta yb apart, so this work will be minus. And if the ring descends by delta yr, this work will be positive. So W of gravity on ring will be small mg delta yr. Now we should need, or we will be in need to find relations between delta yb and delta yr, and that is constant relation. So let us see here. Now we need to know the relation between displacement delta yb of the block and displacement delta yr of the ring. That is the constant relation. So let us explore that one. Here, constant relation. If you see the situation, and I'm showing all these displacement, this block was initially here, it has moved from here to here, delta yb, and ring was initially here, it has moved from here to here, delta yr. String length is constant, so we can write very easily how much block has moved here, that much of length of string has been increased. So this length we can write what? A square plus delta yr square root and minus a will be the increase in length of string between the pulley and the ring. So this will be equal to delta yb. So we may write here the string length is a constant. Thus what we can write here, delta yb is equal to square root a square plus delta yr square whole square root minus a. What is this? You see here, a square plus delta yr square root is this length from Pythagoras theorem. If you subtract a from here, that will be increase in length here, just e, and this increase of length is supplied by movement of this block, so this will be delta yb. So the constant relation was very simple to write here. Now initial and final mechanical energies we can write here. What is initial final mechanical energy? Initial energy is what? Summation ki equal to 0. Why? Because we have considered the ring and the block as a system. So the only internal force is the tension, so no potential is defined for here. So the entire mechanical energy is the total kinetic energy. So initial kinetic energy, mechanical energy is initial total kinetic energy 0. Again, final mechanical energy will be final total kinetic energy, that is also 0, because ring starts from rest and finally it stops. So both these initial and final kinetic energies are 0. Total work done by all the external forces means that is external force means you can say for this system both the gravity are external, the reaction support R was external, N was external. So total work will be W external summation is W by gravity on block plus W by gravity on ring plus W by normal reaction plus W by R. So this will be minus capital Mg delta Yb. This will be plus small mg delta Yr, and this is 0, this is 0. We have seen it earlier. Now we write here minus mg, we substitute the value of delta Yb from this minus a and delta Yr. So in this way we are remaining with only delta Yr, so delta Y will be not there. So by solving this we can find delta Yr. Total work done by all the internal forces. The only internal force is tension, and its work done is 0. So dW internal is summation dW internal conservative plus summation dW internal non-conservative, and that is 0 because there is no internal force. Of course, internal force, there is tension, no internal conservative force, so there is no question of considering decrease in potential energy, and the tension work was 0. Of course, here this tension we cannot say whether it is conservative or non-conservative, but we can say the total work done by internal force is 0. Substituting the expressions obtained in general work energy theorem for a system, we get what the theorem is: work done by all external forces plus work done by all internal non-conservative forces is equal to change in mechanical energy system. So there is only work done by external forces. So this work done by external force plus work done by internal non-conservative force is equal to E final minus initial. So work done by external force, we know this, substitute this, and this term is 0. So what we have, minus mg a square plus delta Yr whole square minus a plus mg delta Yr is equal to 0. And by solving this, what we get, x equal to either 0 or x is equal to 2 MMA upon m square minus m square, and substituting values given here, we can find x is equal to 1.5 meter. That is, I will leave it this calculation to you. Now we use some other idea. Actually, if you see in this problem, total work done by all the internal forces is 0. Yes, and if you include earth, rod, and this support in system, then all the external forces what we have taken, they will be internal. And for this system, we can use conservation of mechanical energy, or we can say we can have block, ring, and earth as system, and for that we can also use conservation of energy. Let us see that idea. B, determine the distance the ring will descend before coming to rest for the first time. And the same problem we are using here. We have just written the statement again. And what solution we are using, just see here. Solution, the idea what we are using, conservation of mechanical energy, what I have just suggested you. And the system what we are taking, block, ring, and earth, rod, and fixed support. All these things we are including in system. So there are no external force, all the forces are internal forces. And why? Out of all these internal forces, what the support reaction R, it will not do any work. Normal reaction from the rod, it will not do any work. Internal force tension, it will not do any work. And internal force, both the gravity, their work can be accounted as change in potential energy. And this is conservative force. So the only internal force which is doing some work is conservative. So total mechanical energy of system will remain conserved. So we can use here. Therefore, there are no external forces as well as no internal non-conservative forces on the system. Weight of the block and the ring are internal conservative forces. Thus, mechanical energy of the system remains conserved. So I have taken a very special problem here. So, and see how we have selected the system: block, ring, earth, and fixed support. Out of these, only gravity is doing work, and that is internal conservative. So only there is no external forces doing work, and all the internal non-conservative forces are not doing any work. Only work are being done by internal conservative forces. So total mechanical energy of system will remain conserved. And now use that idea, conservation of mechanical energy. Applying conservation of mechanical energy, we get, for this we again draw the situation. This system is the initial configuration and now final configuration. And we show the displacement. This is delta YR, how much the ring had descended, and this is delta YB, how much block has moved, and relation between these two we know. So what we can write about from conservation of mechanical energy, total mechanical energy initial is equal to total mechanical energy final, or delta K plus delta U equal to 0. Any of the statement we can use. So I'm using here delta K plus delta U is equal to 0. So what is delta K? No change in kinetic energy. And what is delta U? Increase in gravitational potential here and decrease in gravitational potential energy. So capital mg delta YB and decrease minus small mg delta YR equal to 0. So in this way, what we can write here, substituting the constant relation delta YB is equal to a square plus delta YR whole square root minus a. What we get? Mg, this for this we write here minus this equal to 0, because no need to write here this 0. And by solving this, what we get, x equal to either 0 or this expression x equal to MMA upon capital M square minus small m square. And in substituting the given values here, we can get x equal to 1.5 meter. Now you can see how we can use that is mechanical energy conservation. Now, from all these ideas, what I suggest you to just try to solve and study all these methods at least once or twice, and try to understand how we can use, in what condition we will use mechanical energy conservation, where we should use that is a work energy theorem for a system general form, and when we can use work energy theorem on a single particle. Of course, you will find if there are any non-conservative internal forces at those situations, in those situations, use of work energy theorem general form will be much more easy. Or at that time, if there are only two bodies and the internal non-conservative forces is not doing work on a body, but it is doing work on only one body, in that case we can use work energy theorem on a single particle also, as we have done in the satellite problem and the spring block problem. Because in both the cases, that the internal force was doing work only on the, in satellite problem, the gravity, which was internal force, was doing work only on the satellite. Of course, it is conservative. And in the spring mass problem, the internal force, spring force was doing work only on the block. So in that case, we can use the work energy on a single object also. But what I suggest you, try to solve few problems by all the possible methods. Only when you will be in a position to make your own idea where to use which method. Now we just summarize the idea and just discuss what should be suggested homework for today. And one of the things is again revise all the problems and examples and ideas what we have discussed today. Please revise it very carefully. And suggested homework is from SCB, that is chapter 8 work energy. We have in the previous assignment we have left 3 problems, and just now today I'm including that problem, exercise 19 to 21, and I suggest you to attempt objective 1 and objective 2 of the problem. So we'll meet in the next class. Thanks for patient listening. The words of a language, as they are written or spoken, do not seem to play any role in my mechanism of thought. The physical entities which seems to serve as elements in thought are certain signs and more or less clear images. Albert Einstein.